Hello friends, we are going to continue our discussion on the origin of band gap in 1D lattice. So far, we have seen that a block electron with wave vector closer to the gamma point, which is the origin of the reciprocal lattice, is very similar to free electrons. On the other hand, a block electron with a wave vector equal to the first Brillouin zone boundary is reflected 100% by the periodic potential. We have derived the wave functions in case of 100% reflection. In this lecture, we are going to use the wave functions in case of 100% reflection and relate them to the origin of the band gap. Let us focus on solution at Brillouin zone boundary. That is the wave vector of the block electron is equals to b by 2, where b is a reciprocal lattice point. In that case, the wave function psi of x is e power I dx by 2 plus minus e power minus I dx by 2. Considering the positive sign, we get an even wave function. Psi of ex is cos of dx by 2. Considering the negative sign, we get an odd wave function. That is, psi odd is equal to sine dx by 2. Keeping only one term in the Fourier series expansion of u of x, we get u of x is equals to 2ub cos of dx. If you need any further explanation, you are advised to refer to the lecture on Fourier series expansion of u of x. Potential and probability densities of the even and odd wave function are shown in this diagram. For plotting the potential, I have assumed u of b is equals to minus half. The blue circles denote the location of the lattice points. Let us calculate the kinetic energy of the even and odd wave function. Using the even wave function to be equal to cos dx by 2, the kinetic energy is h cross square by 2m b by 2 whole square. Similarly, using psi odd is equals to sine dx by 2, we get the kinetic energy of the odd wave function to be equal to h cross square by 2m b by 2 whole square. Thus, we find that both the wave functions have same kinetic energy. Now, let us find out the potential energy. Looking at the probability density plot of the even wave function, clearly electron is going to be accumulated near the lattice points. Since a positively charged atomic core is located at each lattice point, the negatively charged electron has less potential energy if the wave function is even. On the other hand, probability density plot of the odd wave function shows that the electron is going to be accumulated in the middle of the two lattice points. That is here. Putting the negatively charged electrons away from the positively charged atomic cores is going to raise the potential energy in case of odd wave function. Let us calculate the potential energy difference between the even and odd wave function in one unit cell. Length of the unit cell is the distance between the two adjacent lattice points. We have to calculate the potential energy for the even and odd wave function, where we assume the potential to be equal to ux is equals to 2ub cos of dx, where b is equal to 2 pi by a. Note that wave functions are normalized considering the length of the unit cell to be equal to a. potential energy expectation value for the even wave function is given by integral 0 to a dx u of x psi e square. So this is equal to 2 by a integral 0 to a, and in place of ux I write 2 ub cos dx, and then mod of psi square is cos square dx by 2. Then rewrite this as 2 ub by a integral 0 to a, and we have this term cos of dx, and then we have 2 times cos square dx by 2, which is equal to cos of dx plus 1 dx, and this is equal to ub by a integral 0 to a 2 cos square dx plus 2 cos of dx dx, and we can write it as ub by a integral 0 to a. So this term is cos 2bx plus 1, and then we have the other term plus 2 cos of dx dx. And now in the limit 0 to a, this integral and this integral, both of them are going to vanish, and then in that case we get the potential energy expectation value to be equal to u of b. Now we already have found out the kinetic energy, thus the total energy of the even wave function is lambda of E, which is the kinetic energy, plus the potential energy u of b. Similarly, potential energy expectation value can be calculated for the odd wave function. This is given by integral 0 to a dx u of x mod psi odd square. This is equal to integral 0 to a, we put the value of the potential 2 ub cos of dx, and then we put the wave function 2 by a sine square dx by 2 dx, which is equal to 2 ub by a integral 0 to a cos of dx, and 2 sine square dx by 2 is 1 minus cos of dx dx, which is equal to ub by a integral 0 to a 2 cos of dx minus 2 cos square dx dx, which we can write as ub by a integral 0 to a 2 cos of dx minus 1 minus cos of 2bx dx. And then if we integrate from 0 to a, this term and this term is going to vanish, and the potential energy expectation value for the odd wave function turns out to be minus ut. We already have found the kinetic energy, thus the total energy of the odd wave function is kinetic energy plus the potential energy. Thus, we have derived that the total energy of the even wave function is lambda E plus UB, where lambda E is the kinetic energy. Similarly, total energy of the odd wave function is lambda O minus UB, where lambda O is the kinetic energy of the odd wave function. Remember that we already have seen that lambda E is equals to lambda O. In the plot, I have used UB is equals to minus half, which implies that the even wave function has less energy than the odd wave function. Subtracting the energy of the even and odd wave function, we get the band gap to be equal to 2 times mod of UB. Thus, band gap is equal to the Fourier component of the crystal potential. Let us try to understand what causes the reflection. In the left-hand side, I show the plot of reflection for different values of U. In the right-hand side, I show the Laue condition of diffraction, and the blue shaded region is a Bragg plane which is located at the Brillouin zone boundary, and a wave is reflected from the Bragg plane if Laue condition is satisfied. We know that Bloch electron is reflected due to the periodic potential. Thus, as U trends to 0, reflection should decrease. For example, take some k point like k equal to 0.5. We see that reflection decreases with decreasing value of U. It is as expected, except when k is equals to Brillouin zone boundary. Here we see 100% reflection irrespective of U value. Remember that Bragg plane is located at the Brillouin zone boundary, and Laue condition for diffraction is satisfied for electron with wave vector k, which is equal to the Brillouin zone boundary. Thus, the reflection that we observe is due to the reflection from the Bragg plane. Finally, let me summarize our discussion on origin of band gap in a 1D lattice. We have seen that periodic potential reflects Bloch electrons. How much of it is reflected depends on the wave vector. When the wave vector is closer to the Brillouin zone boundary, more amount of wave is reflected and less amount is transmitted. On the other hand, when the wave vector is closer to the gamma point, more of it is transmitted and less of it is reflected. Thus, the lattice acts like a filter, allowing waves having k close to the gamma point to pass and reflecting waves with k close to the Brillouin zone boundary. Bloch electrons are like free electrons when k is close to the gamma point. Note that energy of the Bloch electrons coincide with free electrons near the gamma point but differ significantly when k is near the Brillouin zone boundary. When k is exactly equal to the Brillouin zone boundary, Laue condition for diffraction is satisfied and waves are Bragg reflected, resulting two standing waves, one even and another odd. As shown in the diagram, probability density of the even and odd wave function differ. As a result, potential energy of the two standing waves differ. This is what is manifested as a gap in the energy spectrum of the block electrons. Now, let me discuss chronic penny model. This is an alternate way of proving that a periodic potential leads to band gaps in the energy spectrum. Mathematically, chronic penny model is very simple and it avoids many details like Fourier series expansion of the periodic potential, Fourier series expansion of the wave function, and converting time-independent Schrodinger equation to a system of linear equations. Despite its simplicity, the model manages to capture the physics of the electrons in a periodic potential in an elegant manner. Let us approximate the periodic potential by a Dirac comp. As shown in the figure, Dirac comp is a delta function potential at every lattice point. Mathematically, it can be expressed in this form. In a region between x equal to 0 and x equal to a, potential is equals to 0 and the time-independent Schrodinger equation is given by this, which can be written as d2 psi dx square is equals to minus k square times psi, where k square is equals to 2m e by h cross square. Solution of time-independent Schrodinger equation is psi of x is equals to a sin kx plus b cos kx, where k is given by this. Since we have a periodic potential, we can apply Bloch theorem, that is psi of small x plus capital X is equals to e power I k capital X times psi of small x, where capital X is a lattice translation vector. In general, capital X is equals to n times a, where n is some integer. For example, a lattice translation vector can be minus 2a or minus a or 2a, etc. Now, take x is equals to minus a, that is the lattice translation vector is equals to minus a. So, from Bloch theorem, we get psi of x minus a is equals to e power minus I k a times psi of x. In this equation, if we substitute x is equals to x plus a, then we can write as psi of x is equals to e power minus I k a times psi of x plus a. Now, when x is between 0 and a, the wave function is psi of x is equals to a sin kx plus b cos kx. Similarly, when x is between 0 and minus a, the wave function psi of x is given by this. Note that small k in this equation is the wave vector of the Bloch electron, whereas capital K is related to the energy as shown here. We know that the wave function has to be continuous at x equal to 0. How about the first derivative of the wave function? We need to learn one small thing before we can answer this question. Let us consider a single Dirac delta potential given by u of x is equals to alpha times delta of x. This is a single spike at x equal to 0. That is, the potential has a spike of height alpha at x equal to 0, and the potential is 0 everywhere else. Time independent Schrodinger equation is given by this. Now let us integrate the time independent Schrodinger equation. Minus h cross square by 2m integral d2 psi dx square dx plus integral u of x psi of x dx is equals to energy times integral psi of x d of x. Now we set the upper and lower limit of the integral to plus epsilon and minus epsilon. Epsilon is some small number chosen arbitrarily. For example, we can choose this as minus epsilon and this as plus epsilon. Now let us calculate the integral. Minus h cross square by 2m and this is d psi dx at x equal to plus epsilon minus d psi dx at x equal to minus epsilon plus the potential is alpha times delta x and alpha is a constant, so we have alpha integral minus epsilon to plus epsilon delta of x u of x dx, which is equal to energy times integral minus epsilon to plus epsilon psi of x dx. Now this integral involves some delta function and this is equal to alpha times psi of 0. Now we take limit epsilon going to 0. In that case, the right hand side of the integral is equal to 0 and we get minus h cross square by 2m and then this is the difference of the first derivative and this is equal to minus alpha times psi 0. Thus, in the presence of a Dirac delta potential, the first derivative of the wave function is not continuous and the discontinuity is given by this. Now, let us try to solve the actual Dirac-Comp problem. We have defined the wave function between x equal to 0 and x equal to a. Similarly, we have defined the wave function between x equal to minus a and x equal to 0. We know that the wave function must be continuous at x equal to 0. So putting x equal to 0 in the first equation, we get b. Similarly, putting x equal to 0 in the second equation, we get this term. Since we are dealing with delta function potentials, first derivative is discontinuous at x equal to 0. And the discontinuity is equal to 2m alpha by h cross square times b. Let us calculate the discontinuity of the first derivative at x equal to 0. So this is the wave function when x is between 0 and a, and this is the wave function when x is between 0 and minus a. And we know that these two wave functions must be continuous at x equal to 0, and that gives us this equation. Now we want to calculate the discontinuity of the first derivative at x equal to 0, the first derivative is discontinuous because we are dealing with a delta function potential. So from the first equation, we write the first derivative as psi dash of x is equals to a k cos of kx minus b k sine of kx. From the second equation, we write the first derivative to be equal to e power minus I k a k cos of k x plus a minus b k sine of k x plus a. At x equal to 0, the first equation is just a times k, and the second equation is e power minus I k a times a k cos k minus b k sine of k. Now we have to subtract the first derivatives, and they are equal to this term 2m alpha divided by h cross square times p. Now if we divide it by a, then we can just rewrite the equation as k minus e power minus I k a times capital K cos k plus b by a e power minus I k k sine k minus 2m alpha by h cross square is equals to 0. Now from this equation, we can get the ratio of b by a, which is equal to e power minus I k times sine capital K a divided by 1 minus e power minus I small k a times cos capital K a, which can be written in a simpler form as sine k a divided by e power I k a minus cos capital K times a. Now substituting the value of b by a in equation 3, from equation 4 we can write k e power I k a minus k cos of k minus k cos of k plus e power minus I k k cos square k plus e power minus I k k sine square k minus 2m alpha by h cross square sine of k is equals to 0. Now we can combine these three terms and write as k e power I k plus e power minus I k a, and bring the rest of the terms to the right hand side such that 2k cos of k plus 2m alpha by h cross square sine of k a. Now this term is equals to 2 cos of k. We bring k to the right hand side such that we can rewrite this equation as cos of k is equals to cos of capital K plus m alpha by h cross square sine of k by k. This is an important equation and I call it the governing equation for rest of our discussion. Note that there are two k's in the equation. One small k in the left hand side and capital K in the right hand side. Keep in mind that small k is the wave vector of block electrons. Allowed value of small k is given by the periodic boundary condition. On the other hand, capital K is related to the kinetic energy. In the next lecture, I am going to plot this equation and show the existence of gap in energy spectra of electrons in a periodic potential.